All right, so now we're going to put it together and approach some static friction problems. And this lesson will be primarily just working through problems. And remember, there's no formula for static friction, unlike kinetic friction. The only formula we have is for the maximum static frictional force, okay? So getting that direction is going to be correct, and then we might either solve directly for the static friction, or we may use the maximum static friction if it applies in that situation. So let's go ahead and go through a few examples here. So we did this problem before in the last lesson. Contestant pushes his 45 kilogram blocks across a frozen lake. The coefficient of static friction is 0.3 and the coefficient of kinetic friction is 0.1. Calculate the minimum force that he must exert to get the block moving. So we got to overcome the maximum static frictional force to get it moving, right? So let's do our free body diagram. We have gravity. We have this F force pushing down here like this. We have a surface here that exerts two forces, a normal force, and then the static frictional force from the previous lesson we talked about for this exact scenario, it's pointing to the left like this, right? And so we have this here. This angle is 25 degrees, and we know the acceleration is 0. Why do we know the acceleration is 0? Well, I want the minimum force. That means I don't want, like, yeah, Superman could slam this thing, it could accelerate very fast, but if I want the minimum force, I need the acceleration not exactly 0, okay? Because you might argue, Alan, it's got to move a little bit. It's got to go from 0, it's got to have some acceleration. Close to 0, almost 0. Not exactly 0, but we'll just say 0.000001 meters per second squared. So close to 0, but not exactly 0. But for all intensive purposes, like say about 0. Anything greater than that, then it would be slightly accelerating, right? So then we're going to decompose this, right, into F cosine 25 degrees and F sine 25 degrees. And if we want this to accelerate, this here needs to be the maximum static friction. So we are going to use the coefficient of static friction in this case because this guy's got to be the maximum static friction. Why? Because I do want to get it to move. So it needs to be just enough friction, the maximum amount, and if I just go a little bit more, then I'll overcome the static friction and it will begin to move. So then we do F net equals MA, which is 0 in this case. For the x direction, we have F cosine 25 degrees pointing to the right. We have force of friction pointing to the left. That's 0. And in the y direction, we'll say up is positive. Sorry, didn't say which way is positive. Say Fn is positive, mg is negative, and F sine 25 degrees also negative. That equals 0. Here we can calculate what the static frictional force will be mg, because why am I solving for the static frictional force? Is because the normal force is because I'm going to need that in here. And I don't know what normal force is not a variable that I know the value for. So this is mu s times normal force, because this is maximum, right? Again, max static friction equals 0. So that means F cosine 25 degrees minus mu s times Fn. Place it with this guy, mg plus F sine 25 degrees equals 0. And at this point, it's a math problem because I know all of the numbers other than this, right? Like I know what mu s is. I'm going to distribute the mu s minus mu s mg, distribute it to both of them, minus mu s f sine 25 degrees. I'm going to move the mu s mg to this side. I'm going to factor out the f out of these two terms. And then I will divide to solve out f, right? That's the main idea there. And you just plug in the numbers. We know mu s is 0.3, we know m, we know g, and then you just plug in numbers there. Okay, let's do one like this. Actually, I'm going to skip this one. It's a very similar problem. Let's go to a more complex problem like we did last one, like this one here. Assuming the block has this, right, has a mass of 6 kilograms, coefficient of friction between the block and the wall is 0.4. What is the minimum force needed to keep the block from sliding down the wall? Right, so we're going to draw our free body diagram here. We're going to have mg. What's touching it? We have F pushing it to the right. What else is touching it? We have the surface here that exerts two forces, a normal force, and like we talked about in the last lesson, we're going to have a static frictional force that's going to oppose that. Now again, because it's held in place, we're preventing it from sliding down the wall, the acceleration is 0. So we know if we set right positive and up positive, right, then in the y direction, frictional force minus mg is going to equal 0. So the frictional force will equal mg because the acceleration is 0. And in the x direction, F is to the right, normal force to the left, that's equal to 0. So this force is equal to Fn, right? So standard process, I'm just going a bit faster because by now, hopefully you understand the problem-solving process when it comes to forces. Now, if we're going to say at this point, because it's the minimum F needed, right, what happens when I make F smaller and smaller is the normal force will get smaller and smaller. And the frictional force maximum is mu times F, mu times the normal force. So if I shrink this guy goes down, the maximum static frictional force will go down, and eventually it will be smaller than mg. So mg will then pull it down more. So if you ever think about like an example, let me just show you. Like I have take my calculator, and I'm holding it against the wall. Let's put it over here so you can see it. I'm holding it against the wall here, right? I'm pushing against it. But if I don't push enough on it, if I push less and less and less and less, eventually it will slide down, okay? And so what's happening is we're reducing the normal force from the wall, right? The wall exerting less normal force, and that's reducing the maximum static friction, and eventually it goes below the mg amount, and then it will accelerate downward, right? So if I'm just the minimum to hold it means I just need enough for the maximum static frictional force to equal mg. And then replace the Fn with F. Then the F min we're going to have here is going to be mg over mu s like that, right? And just plug in the number, 6 times 10 divided by 0.4. Okay, let's look at this problem. Block A has a mass of 10 kilograms, sits on an inclined plane, but is not moving. Calculate the force of friction required to keep the block from moving. Okay, now I didn't give you a static frictional coefficient, right? But I could have given you one. But you wouldn't need it in this case because here's mg. And then what else is touching it? Well, we just have a surface, right? That exerts two forces, a normal force. And then which way is the static frictional force? Well, if there were no friction, this thing would just slide down the ramp, right? So friction has to prevent that sliding, so it's pointing up the ramp. Cool. Let's identify the acceleration. Acceleration is 0. Let's go and list our x and our y axis because the frictional force is parallel to the ramp. Let's just go ahead and make this 20 degrees here and decompose it. This is our x and our y direction, right there and there. So this is mg cosine 20 degrees. This is mg sine 20 degrees. And because the acceleration is 0 in the x direction, we'll say up the ramp is positive and out of the ramp is positive. So force of friction up the ramp is going up. Mg sine 20 degrees is going down. That's equal to 0. Look at this. I already know the mass. I know g. I actually know the answer. The frictional force needed is going to be mg sine 20 degrees. Right? I don't need to solve anything else. 10 times sine 20 degrees. Right? You're just going to plug that in there and get a number. Right? That's it. That's the setup. Didn't require maximum static friction because it wasn't necessarily maximum. Maximum, like presumably this is what's necessary to keep it there. Whether that's equal to the maximum or less than the maximum depends on what the coefficient of static friction is, but it's not necessarily mu s times Fn, right? So you never want to look at this problem and say like, oh, it's mu s times the normal force. No, that would be only if it were the maximum static frictional force, right? So I have a block of mass 12 kilograms in inclined plane. This is 30 degrees. Coefficient of static friction, we'll say static friction, is 0.1. So the plane is inclined 30 degrees. What's the minimum and maximum value F that will keep the block from moving? So why is there a minimum and a maximum? Let's start with maximum. What happens if I push too hard? Well, let's draw a free body diagram. We'll do the frictional port last. So we have mg, we have an F pointing to the right. We have another, what's touching it? We have a normal force from here. And then we have a static frictional force. Now, here's the thing. If it's the maximum, that means if I exceeded this, if I had a bigger F, what's going to happen is that without any friction, it would go up the ramp, right? Because if I exceed it, if I push harder, it's not going to go down the ramp. It's going to go up the ramp. So static friction's got to be parallel to the ramp, parallel to this surface, and going down the ramp for the maximum F calculation, right? The maximum, because if I exceed it, like if there were no friction, it would slide up the ramp in that case, right? And so this is why that the option 1 is better. If you go back to the previous lesson, why option 1 is going to be better in this case, because if I ask you this without friction, which way is going to slide, could go up the ramp, could go down the ramp, right? Kind of depends on what the F is. But for maximum F, it would go up the ramp because you would have more than enough to overcome gravity, because you need to overcome friction as well. Okay, so then let's align. Our acceleration is 0 because it's not moving. The block's still not accelerating. So then we'll decompose x and y like this. Now in this case, because again, should you decompose the normal force of frictional force, it's more common to probably do it this way, but you don't need to rotate the axes given that the acceleration is 0, but it's probably easier and more common to do it this way. So then this would be f cosine 30 degrees. This would be f sine 30 degrees. And then the mg has to be decomposed into mg cosine 30 degrees and mg sine 30 degrees. Right? Okay, the acceleration is 0, so in the x direction, all the upward forces equal the downward forces, so we'll go up the ramp is positive. So that means f cosine 30 degrees minus the force of friction, and then mg sine is also pointing down, minus mg sine 30 degrees equals 0. And then the other equation we get over here is going to be in the y direction. We have the normal force. We'll say this way is the positive direction. Normal force is out of the page. Then the mg cosine 30 degrees is, sorry, not out of the page, out of the plane, into the plane. And then this is the negative y direction also. Minus f sine 30 degrees equals 0. Now I'm trying to figure out what f is. This case, the F is this equal to the maximum static friction because it's the maximum F I can apply. So we want the friction to be at its maximum, right? Because that's what's preventing it from going up. That's equal to mu times the normal force. So we can replace the frictional force with minus mu Fn minus mg sine 30 degrees equals 0. Now I have two equations, two unknowns. What you want to think about is I don't know the normal force, so I want to get rid of the normal force in some way, right? And then plug that into here. So we're going to solve for the normal force here. It's going to be mg cosine 30 degrees is equal to f sine 30 degrees, plus f sine 30 degrees. And we're going to take that normal force and plug it into here. So we'll get f cosine 30 degrees minus, and let's just distribute the mu to all of these, minus mu mg, actually I just put parentheses, cosine 30 degrees plus f sine 30 degrees, okay, minus mg sine 30 degrees equals 0, and then we're going to solve for f here, right? The f is what's unknown, so we're going to take that mu and distribute it so that we can just combine the terms with f alone, right? So it's going to be f cosine 30 degrees minus mu mg cosine 30 degrees minus mu f sine 30 degrees minus mg sine 30 degrees equals 0. Everything without an f, because we're solving for f, goes to the other side so we can factor out an f. So the right side is going to be the sum of these two, mg sine 30 degrees plus mu mg cosine 30 degrees. And then what's left is these two terms where we can factor out an f. Minus mu, oops, not minus f. I factored out an f out of this guy, minus mu sine 30 degrees. And then we'll just divide this thing over. Okay, so that gives you the maximum f. This is the maximum f here that is necessary. So I just divided this guy over, right, down to there. Okay, now let's do f min. So what's different between the minimum f? Well, now you need to think about what if the force were 0? Like, what's going to be different about the scenario? I'm going to just go real quick that you can work this out. But if we're at the minimum and there were no friction, then, or think about when the f is 0, it's just going to slide down the ramp, right? Minimum, the smallest is going to make it 0, right? So if it's 0, then what that means is the static friction slides down the ramp. The static friction is helping me. So the difference between this scenario and this scenario is the direction of the static frictional force. This one was up the ramp. This one was down the ramp. So everything actually is going to be the exact same if you think about it. If you want to shortcut this, I would think of it as an exercise that you go through to give it a shot, because there's other examples I want you to see. But just think about like this f, all we're going to do and I'll just highlight it here, is we're going to make this a plus instead. So this will be a plus, and that will change. Let's see, this part doesn't change. Only this part changes. So instead of it being, you would make this a plus instead. So if that's a plus, then this will be plus, this will be plus, and then when you move it over to here, this will be now a plus, and then this would be a minus instead, because this is positive. We bring it over. Go through the exercise on yourself. I don't think it's super challenging, but just see the fact the changing of the direction, how that's going to change the number, and it's going to make it smaller if you do the computation and plug in the numbers there, okay? Because the numerator gets smaller and the denominator gets bigger. So overall, it's going to give. Okay, 2 blocks are stacked below and rest on a frictionless surface. There's friction between the top 2 blocks, static coefficient of friction mu, and external force is applied at the top block at an angle theta. What is the maximum force that can be applied for the 2 blocks to move together? Move together in this case is they're going to have the same acceleration, same kinematic variables, because they're going to have the same motion. In particularly the acceleration. So they're both going to accelerate to the right A. Let's draw a free body diagram of M2. Okay. So this is why static friction doesn't mean the acceleration is 0. This is why I picked this problem. Static friction just means there's no rubbing against it. They're going to, see, you're going to push on this guy and going to slide. So this is a tricky one. Actually, let's do a free body diagram of M1, actually. So, because M1 is probably easier to do first. So first you're going to have M1G, gravity. Then what's touching it? You have this F going down at an angle theta here. What else is touching it? The surface here, this normal force between M2 and M1, because there's 2 forces. A normal force, we'll call it on block 1. Okay, and now there's a static frictional force. Now, which way is it going to go? Well, imagine that there were no friction. See, the acceleration we already know is to the right, so it being to the right doesn't make sense, because maybe this F to the right is causing it to go to the right. So the option 2 of identifying the acceleration is quite tricky in this scenario, because knowing the direction of the acceleration is not going to necessarily tell you which way the static frictional force is pointing. So this is why I go with option 1. I think about if there were no friction, then this guy would move and this guy would not move, because ultimately the only way this guy moves is because there's some friction to the right. Okay, so imagine that there were no friction. This block would just slide to the right, right? If this was super slippery, there's no reason that the M2, it'd be like I'm on top of an ice block and I push this thing, the ice block's not going to move, right? Like, because it's so slippery up top. So then this guy moves to the right, so that means the static friction is opposing that and to the left. Okay, cool. That's free body diagram for M1. For M2, let's draw a free body diagram. We have M2G. There's friction between the 2 blocks. There's no friction here, okay? So what's touching M2? You have this surface. This surface doesn't have any friction, so we'll call this FN2. This surface doesn't have any friction, so there's no horizontal force from that guy. What else is touching it? M1. So that exerts a downward force. That's a third law pair, right? M2 is pushing up on M1 with FN1, so M1 is pushing down with the same equal and opposite FN1. And then this one you can use option 2 to decide, but there's a few ways to think about this. The static friction is going to point to the right. There's a few reasons why it has to point to the right. One, it's due to Newton's third law. If there's a leftward force from M2 onto M1 due to static friction, then there's an equal and opposite rightward force onto M2 from M1, right? So if M2 pushes left on M1, then M1 pushes to the right on M2. That's the Newton's third law. Second thing, we know the acceleration is to the right. There's only one horizontal force acting on M2 that's touching M2. Not F, because F is not touching M2. Only the static frictional force could be acting and going to the right. Okay? Third is the option 1 is to say, like, well, without any friction, M1 would slide to the right, right? And so M2 would oppose that sliding. From M2's perspective, he's sliding to the right, so he's going to want to exert a force to the right to compensate for that. Okay, so either way you want to think about it, that's the scenario. That's the free body diagram. Again, the trickiest part probably in static friction is to set up the free body diagram. Now let's do it. Now we want the maximum friction force that we can apply, which means we do need to continue our process here. So this angle is theta. This is F cosine theta. This is F sine theta. Okay, and now let's do net force equals ma. Now the acceleration is to the right. It's not 0. Is to the right. So for M1, if we do the x direction, we have F cosine theta to the right, we have frictional force to the left, that's equal to M1 times A. And in the y direction, we're going to have Fn1 pointing up, we're going to have F sine theta pointing down, and we're going to have M1g pointing down, and that's equal to 0, because the acceleration is not in the vertical direction, only in the, and this is me assuming right was positive, and up was positive. Okay, let's go back to M2 over here. Let's look at this guy, his x direction. Well, he's going to have a frictional force to the right. That's equal to M2 times A, so that one's pretty easy. The y direction, if we say up is positive, then we're going to have Fn2 pointing up. We're going to have Fn1 pointing down. We're going to have M2g pointing down, and that's equal to 0, because the acceleration, again, is in the horizontal. The x direction, there's no y component to that acceleration. Okay, now we know that if we want the minimum F, maximum F necessary, then that means what happens if I exceed that maximum is it's going to slide. M1's going to slide. M2's not going to be able to keep up, right? Because this would hit a maximum value. So what's going to happen is at max F, the frictional force is equal to the maximum, which is mu Fn. Fn1. Now, which Fn? Because there's two normal forces, Fn1 or Fn2. Well, it's the normal force on the surface that has friction. The normal force that has friction is Fn1. This table doesn't have any friction, so Fn2 has no friction. It's the normal force between the two surfaces where the friction is acting, right? So mu times Fn1, that's going to be mu times, let's solve for Fn1 over here. Fn1 would be M1g plus F sine theta. So that's going to be mu times M1g plus F sine theta is going to be our force of friction. So that means in the x1 over here, we're going to have F cosine theta minus mu M1g plus F sine theta equals M1a. And on this guy here, we have FF equals M2a. That's mu times M1g plus F sine theta equals M2 times the acceleration. Now I want to know the here's the thing is I can't just add these up. Well, you can't add these up. You'll negate them out, but like I have a couple, but then the F is unknown and the acceleration is unknown. Like I don't actually know what the acceleration is, right? So that isn't sufficient to work that out. So we got to think about when you're having a lot of symbolic problems. So this is a tricky thing when you have a lot of symbolic variables here on what you're solving for. You got to think about what are your knowns, or actually, most importantly, the unknown number of unknowns we have. Our unknowns are F and acceleration. If you think about all of these, we're given the masses, we're given G, we're given the thetas. We need to figure out what F is. So we want to get rid of the acceleration, ultimately. That's our goal. So how do we want to get rid of the acceleration is you could divide by M2 here and then plug that into here. So then you have F cosine theta minus mu. So if you get stuck on these symbolic ones as to what to do, think about what the unknowns are. You have enough equations and enough unknowns to solve this. This is M1 over M2 times mu M1g plus F sine theta, like that. Okay. And so what we want to do now is solve for F. Kind of an annoying problem, I'm not going to lie. Like it's definitely like kind of a lot of tedious, but we have F's here, we have F's here. We need to distribute some things and then combine all the F terms together, right? So minus mu M1g minus mu F. This is me distributing the minus mu to both terms. And then this guy, we got to distribute both of these over here as well. Minus mu times the F sine theta. This is M1 over M2 mu M1g plus M1 over M2 mu F sine theta. We want to put all the F's together. So this guy over here needs to move to this side, and this guy over here needs to move to this side, right? So that the left side has only F's. Okay, minus mu F sine theta minus M1 over M2 mu F sine theta. That's equal to M1 over M2 mu M1g, and this guy moved over plus mu M1g. Okay, and so then we're going to factor out an F here. It's just an algebra exercise at this one. Mu sine theta minus m1 over m2 mu sine theta equals this. You can factor out if you wanted, factor out a mu m1g times m1 over m2 plus 1. And then just divide this whole term over. Move that over, and that would give you the F there, okay? Don't focus on the algebra part. Don't get stuck on that part. The setup is the much trickier part. You get to this point, you've done 95% of what is really needed. The rest of the algebra is just you focusing on algebra skills to get to the final answer. But a huge portion of what you're evaluated on is whether or not you can even do this setup correctly.